So I will resume from where we stopped the last time on the fundamental concept of universal property, which is actually the key concept of category theory. Let's recall that category theory introduces a new paradigm for thinking about mathematics, which is based on a relational approach to mathematical structures. So the idea is to understand mathematical structures and even define them in a certain precise sense that we shall clarify by means of the relations that they entertain with other structures of the same mathematical environment formalized as a category. So the idea is really to express the kind of relationships that are sufficiently strong to determine an object as a universal one satisfying them. So last time, in preparation for the introduction of this technical notion in full generality, I have already introduced some specific examples of universal properties, definitions of familiar constructions from set theory. We reviewed the construction of the Cartesian product of two sets, or more generally the fiber product of two sets over a third one. We reviewed them from a categorical viewpoint, and we pointed out that they satisfied properties that are sufficiently strong as to determine these objects together with their canonical arrows relating them to the objects of the relevant diagram, sufficiently strong to determine this object up to isomorphism. So now I'm going to give you the full technical definition of this notion. So the technical embodiment of this idea of universal property is given by the notion of limit of a diagram in a category and the dual notion of colimit. So in order to define limits and colimits, one has first to formalize the notion of diagram in a category. So intuitively, what is a diagram in a category? Well, the idea is that if we have a category C, a diagram in C will be a collection of objects in C related by arrows. So if you think a moment about this, you realize that this notion of diagram can be formalized in terms of functors taking values in the category. So we can think of a diagram.
Could you use maybe
yes, maybe it's better. Okay. So if we want to formalize this notion of diagram, we can take just functors taking values in this category, and the source category will define the shape of the diagram. So for instance, if you want to consider like two objects in a category without any relation between them, what you take is the category consisting of two objects and only the identity arrows on them. So it is the discrete category on a two-element set. And you see that functors, so if we take J to be this category here, of course, the datum of two objects in C is the same thing as a functor from J to C. And of course, if you choose categories of like source categories of different shapes, for instance, you can take a category where you have two objects and two parallel arrows like this, and of course you should always put the identities. Then what will be a diagram of shape J in C? Well, it will be just a collection of pairs of objects related by arrows like this. Okay. So, of course, here I have taken two very simple shapes, but of course you can take arbitrary shapes. So if you want to formalize the notion of diagram in full generality, you just take a functor. Okay, now that we know what a diagram is, we introduce the notion of cone over such a diagram. So a cone is the datum of an object, which is the vertex of the cone, and for each object of the source category of the diagram, an arrow which goes from the vertex of the cone to it. And of course, because the objects of the source category can be related to each other by arrows in the source category, one requires some compatibility conditions relating these arrows. So one requires, more precisely, that all the triangles of this form commute. So this is the notion of cone. Now, if we want to formalize what it is a cone, here I have just given an intuitive description, but formally we can define a cone as a natural transformation from the diagonal functor applied to the vertex of the cone. So a natural transformation from this to the given diagram. Because if you So if you write down what a natural transformation from delta of C to F is, you find out precisely the commutativity conditions which define the notion of cone. So, of course, this construction of delta of C makes sense for any C, and so it defines actually a functor which is called the diagonal functor, which goes from C to JC. So this is the diagram which sends everything to C, and if you have arrows like in the source category, they are sent to the identity on C. So you see that actually this is an instance of a naturality condition where, you see, you can write this triangle as a square, where here you have C, C, the identity, and then this, which is in diagonal, becomes in vertical. Okay, very good. So, what is a limit? Well, a limit is a universal cone, in the sense of the next definition. So, a limit for the given diagram, for the given functor, is a cone such that every other cone over the same diagram factors uniquely through it. So the condition, if we want to like express it concretely, is this. So normally we denote the vertex of the limit cone like this, by writing lim of the given diagram. And then if we have the arrows, which are the legs of the cone, here so the universal property of the limit cone is that for any other cone over the same diagram, so here we will have so bj1, bj2, there should exist a unique factorization. of, so a unique arrow from the vertex of this cone to the vertex of the limit cone, which make all these triangles here commute. So remember what we had with the Cartesian product. The Cartesian product, here we had J, like the source category, just the discrete category on two objects. Because we don't want any relation between A and B. And then you see that the universal property that we stated last time was a particular case of this general definition, you see, because for any pair of arrows from C to A and C to B, we could find a unique arrow from C to this, which makes these two triangles commute. So you can see how this very general definition specializes to what we saw last time. Okay, last time we also talked about the duality principle in category theory, which allows you to dualize notions that can be formulated abstractly in the language of category theory. Because the notion of limit, of course, can be expressed in that language, we can dualize it, and we get the notion of colimit. Now, concretely, what does it change? Well, it changes just the direction of these arrows. So instead of having arrows from this to the objects of the diagram, you have arrows going in the other direction. And also, the arrows connecting the vertices of the cone should go in the other direction. So remember that when you go from a category to the dual one, you keep the same objects, but you reverse the arrows. So if we want to give a concrete example of a colimit,
Sorry?
yes?
Just to make sure that the C that you drew here corresponds to the C prime in your definition.
The C for any, oh, yes. Yes, because I had chosen, yeah, so, okay, yes, so basically, this is a C and this is C prime. Sorry, it was a bit confusing. Okay, so concrete example of a colimit. So we can take J to be always the discrete category on two objects. But this time, instead of taking the limit, we take the colimit. What do we get? In particular, does such a colimit exist in the category of sets? Yes, it is given by the disjoint union of A and B. And we can immediately realize about this because we have, first of all, two canonical maps which go in this direction. And what we have is the dual of this property. So for any pair of arrows from A to C and from B to C, there exists a unique arrow here, which makes these two triangles commute. So you see that we can actually build this kind of colimit in the category of sets, and it corresponds to a very natural construction. So in particular, we see that another familiar construction from set theory can be entirely captured in categorical language. And in fact, I can anticipate that it is the case for essentially all the fundamental set theoretic constructions. Also, quotients of sets by equivalence relations can be captured categorically, as we shall see, by using a particular kind of colimit, the notion of coequalizer. But before introducing this, let's introduce other fundamental notions. So the notion of colimit or limit preserving functor. Well, if we have a diagram in a category, and a functor going from that category to another category, it makes sense to introduce the notion of co-limit preservation by that functor. So we say that such a functor preserves the limit of the diagram if by composing this functor with the limit cone gives a limit cone for the composite functor. So it is really the intuitive notion. Yes?
What's the reason for finding the limit of a functor and not like the limit of a diagram in a category as like an element and morphism based on the idea of, I mean, the fact that you use the idea of functor itself to interpret the diagram.
Yeah, it is motivated just by purity of methods in the sense that by expressing all the notions in the same language, your technique becomes more natural. Of course, you could more generally define a diagram as by using like the underlying graph of the category, so you could forget like the categorical structure if you want, but because of the fact that you can always build the free category on a graph, basically the level of generality is the same. And so it is more convenient not to introduce several different mathematical languages for talking about notions that then we want to compare with each other. So you see, we want to exploit the fractal properties of categories in a sense. And so we have an interest in remaining within the same mathematical language and formalism. But your point is correct. I mean, in general, you could completely forget the composition law and just think of a category as a graph, and then a diagram will be a graph morphism from a graph which specifies the shape of the diagram to the underlying graph of the category. You could do that, but it has the same level of generality. Okay, good. Fundamental remark, universal properties, as we said at the beginning of the lecture, determine the objects that satisfy them up to isomorphism. And this you can immediately see because you see a universal property gives you this existence and uniqueness conditions. So if you had two things satisfying the same universal property, by applying the universal property to one and then to the other, you would get two arrows between the two vertices. And then the composite of these two arrows, by the uniqueness requirement, should be the identity. Because, of course, the identity, if you take the same cone, you see, it makes trivially all the triangles commute. So from this you see immediately that universal properties are strong enough to determine the objects that satisfy them up to isomorphisms. So they can be used to give definitions of what is a categorical product or a categorical coproduct, which is just this universal property in the case of a discrete diagram. And many other notions that we shall encounter. Of course, you see here the criterion of equality is not the same as in set theory. In set theory, you consider two sets the same when they are equal. In category theory, you consider two objects the same when they are isomorphic. But it makes a lot of sense. If you think about what happens in universal algebra, for instance, when do you consider two groups the same? When they are isomorphic. After all, if two groups are isomorphic, they should really be considered the same from an algebraic point of view. So in a sense, it is a set theory which is quite unnatural with respect to the usual mathematical practice. Category theory is much more natural because after all, what really matters in the mathematical work is the behavior of objects, not really the specific coding that you use to express them in some formal language. Okay, now we discuss some specific examples of limits and colimits. What do we get if we take as source category the empty category? Well, if we take J to be the empty category, then of course there is just one diagram defined on the empty category. It is the empty diagram. What is a cone over such a diagram? Well, it is just an object, the vertex of the cone, because you just have the vertex and nothing else. And what are such cones that are universal? They correspond to the so-called terminal objects. So an object is terminal in a category if for any object of the category there exists exactly one arrow from that object to it. So if we look at what happens in our familiar category of sets, we see that terminal objects are given by singleton sets. Because, of course, if I take a singleton, for any set, there exists exactly one arrow in the category of sets, namely one function from that to that. Of course, an object is a terminal if and only if it consists of a single element, because if I have more than one element, I could choose an A for which I have more functions between them. Okay, so again, this is an illustration of the possibility of capturing the property of a set being a singleton in categorical language. Okay, then, of course, if we dualize this notion, we get the notion of initial object. What is the initial object in the category of sets? It is the empty set. If we take the empty set, it has the property that for any set A, there exists a unique arrow from the empty set to A. It is the empty function. Good. Now, second example, the case of a discrete category, which we have already encountered here and there. Here in the case of limits and here in the case of colimits. So in the case of a general discrete category, here I have taken a discrete category on two objects, but of course I can consider discrete categories on an arbitrary number of objects. In this case, limits are called products and colimits are called coproducts. Again, what happens in sets is that this notion specializes to that of Cartesian products. And in the case of coproducts, arbitrary disjoint unions. Okay, now we discuss how to recover the universal property that we had considered last time in connection with the notion of fiber product of two sets over a third one, how to recover this as a particular case of our general definition. So we have to specify the source category J. So how do we define it? We take three objects related by arrows as specified on the slides. Now I will draw them. Okay, so we take a category of this shape. We have three objects and arrows connecting them like this. So two objects which are sent to a third one, like this. Of course, you recognize that this is the right category to consider in order to think of a datum like this as a diagram in the category of a shape this. So this is the situation that we had considered last time. So I told you that the fibered product of these two sets over C satisfied a universal property, which was this. For any pair of arrows making the outer rectangle commute, there exists a unique arrow here making these two triangles commute. So you see that the universal property that we talked about last time is just the particular case of the universal property of limit for this particular shape here. Good. Then we also talked about this construction of the so-called equalizer of two functions, two parallel functions. So you see, if you have two sets A and B and two functions between them, f and g, what you can do is to consider the subset of A consisting of the elements where the two functions agree. And this construction also can be captured by means of a universal property, which is the following. So for any arrow k such that f composed with k is equal to g composed with k, there exists a unique factorization of this arrow through this inclusion. And you see that actually this is a particular case of the notion of limit where we take J to be the category of this shape. So two objects and two arrows between them and the identities. Okay, good. So I think that, yes. Yes. For a category, yes, I mean it's the object itself. So if you you see, it's a particular case of that, where you take the discrete category with a single object. So it is the object itself. You have nothing. Yeah. Okay, good. So I think that these examples already illustrate the interest of this very general notion of limit. And similarly, by dualizing and specializing the notion of limit, we can get many other interesting notions. So I would like in particular to discuss the notion of co-equalizer, because we are going to use it to construct arbitrary colimits in the category of sets. So it's good to start familiarizing with it. So co-equalizer is the dual of the notion of equalizer. So abstractly is this. So we have a pair of parallel arrows, and the co-equalizer is an object together with an arrow Q, such that Q composed with F equals Q composed with G, and in fact it is the universal one co-equalizing F and G, meaning that if we have any other arrow K which does the same, it should factor uniquely through it. Okay, so remark, if R is an equivalence relation on a set X, then if we consider the two projections from R to X, and we take the projection map here to the quotient, we realize that actually this is a co-equalizer diagram. Because suppose that you have any other function that takes the same value on elements related by the equivalence relation R, then it should factor uniquely through the quotient. So, as you can see, another very important mathematical construction, the construction of quotients, can be captured categorically. Okay. Now, let's look at how we can build arbitrary limits and arbitrary colimits in the category of sets. So this is a course about topos theory, and actually the basic topos is the category of sets. So if we want to understand arbitrary toposes, we should definitely start from the topos of sets. So this is what we are going to do concerning limits and colimits. Once we have understood how limits and colimits work in sets, we will be able to understand how limits and colimits work in categories of pre-sheaves, and then from this we will be able to understand how they will work more generally in categories of sheaves, namely Grothendieck toposes. So we will proceed step by step. So let's start constructing arbitrary limits in sets. So this, I have called it a theorem, but actually it's an easy exercise. So you can check that you can build the limit of a diagram in sets by taking the equalizer of a pair of arrows between two products, one indexed by the objects of the category, and the other indexed by the arrows in the category, and which are defined by two natural conditions. Now, to clarify this, I will write here a few details. So the interest of that result is that it allows you to build arbitrary limits in a category which possesses them, just in terms of products, arbitrary products and equalizers. And then we will have a dual result for colimits. We will see that colimits dually can be always built from arbitrary coproducts and coequalizers. So in fact, this result I formulated for sets, but it holds more generally for any target category in which such coproducts, in which such products and equalizers exist. So for concreteness, I'm presenting this for sets, but you should know that it works more generally. Okay, so what do we do? So we first consider these two big products. And we realize that there are two canonically defined arrows between them, which are specified by the universal property of these products. You see, by the universal property of this product, giving an arrow to that is the same thing as giving the composite with the projections. So here I call the projection corresponding to U, pi U. So what I have to specify is simply the composite So what you can do is, for defining A, you take here the projection corresponding to the object J. And this is what is called pi prime J. To define B, you take the arrow to h of J, which is given by the composite of the projection to h of I, followed by h of u. So this is how B is defined. And if you take the equalizer of A and B, you realize that it clearly satisfies the universal property of the limit. So do it as an exercise. It's quite easy, but it's instructive. Okay, now we dualize, and we get the construction of colimits. So you see that what happens here is that instead of taking products, because we dualize, we take coproducts. And so instead of taking equalizer, we take co-equalizer. So in fact, if you prove the result not for sets, but for an arbitrary category here as target, you can actually prove the result just once and then apply the duality principle. Of course, you see, if we formulate the results concretely for sets, we have to prove to give two separate proofs. But in fact, these results, as I mentioned, hold more generally for any category, any target category in which equalizers and products exist, or respectively co-equalizers and coproducts exist. Okay. So a note here: if we want to build the co-equalizer of a pair of arrows, so we discussed the particular case of an equivalency relation, but if we don't have an equivalency relation, basically what you have to do is to generate it to build the co-equalizer, because you have to take the quotient of the target set by the smallest equivalency relation containing all the pairs of the form f of a, g of a. Okay, now that we have understood how limits and colimits can be computed, in particular in sets, we consider the general case of a functor category. So, in fact, what we are primarily interested in is categories of pre-sheaves, which, let me recall, are controvariant functors on a category with values in sets. So we will be particularly interested in categories of this form. But in fact, we can prove this result, which tells us in full generality how limits or colimits in functor categories can be computed from limits or colimits in the target category. So the idea is this. So suppose you have a diagram with values in a functor category. Now, a functor category is related in a very natural way to the target category by means of evaluation functors, which are indexed by the objects of the source category. Because what you can do is, for any fixed object C of the source category, you can consider the evaluation of the given functor at the object C. Of course, this is functorial because if we have a natural transformation, namely an arrow in this category, from a functor f to a functor g, by evaluating, we get the component at the object C of this natural transformation. So it is a well-defined functor. So the idea is to use this collection of functors, because of course I have one of such functors for each object of the source category. So the idea is to use all of them together to and the limits or colimits that we suppose to exist in D to construct limits or colimits in CD. That's the idea. So basically, things are quite trivial because it turns out that if I have my diagram H and I compose here with the evaluation functor, and so I obtain this, what I have is, so suppose that limits exist in D, or at least that limits of these particular diagrams exist in D, what I can do is, for any C, I take the limit of this composite functor. And it turns out that this is functorial. So it defines an object of this category, which is actually the limit of the functor H. So if I go from C to C prime here, I have, the universal property of limits give me an arrow here, and therefore I get an object of this category, namely a functor from C to D, which you can show satisfies the vertex of a limit cone for H. So again, it's a very routine verification to make. Again, it's instructive for you to write all the details for learning and get familiar with this language. Okay, so because we know, so this works for limits as well as colimits, of course. Again, it's an abstract result that is stable under dualization. So it works for limits as well as for colimits. We will be particularly concerned with categories of this kind. So by choosing D to be the category of sets, we are quite comfortable because we have just seen that in sets, limits and colimits always exist, for whatever shape we choose. You see, it's marvelous to be able to always construct objects satisfying these universal properties. Okay, so we know, in particular, thanks to this result, how to compute limits and colimits here in this functor category. So this way of computing limits or colimits is called pointwise computation. Pointwise in the sense that I can fix the point, the object of C, and compute object by object, the limit or colimit, and then put them all together by using the functoriality property. Good. So, yes.
To come back on the previous slides.
Yes. Yes.
Means that just for any functor or diagram, as you explained, it's connected in itself to the notion of product, right?
Yes, if you want, I mean, you can use products, if they exist, to build the limit of that diagram. So it's not the diagram itself which is connected to products, it's just that in order to build its limit, you can use products in that way. Yeah. No, it can be infinite, and indeed it's very important to work with infinite diagrams as well. In fact, a topos is a kind of category which is obtained from very concrete, possibly finite categories by adding all possible colimits, infinitary ones. And it's very, very important to allow infinitary operations in order to get good closure properties. It's like in topology. You see, in topology, there is a fundamental operation, which is the union of open sets. You don't require unions to be finite. If you wanted to restrict to finite unions, you wouldn't do topology. Topos theory was born out of a desire to go beyond topology. In particular, you should keep at least this fundamental infinitary operation, which is really crucial for topology. And so as we will see, toposes provide really a very, very general abstract notion of space, but the basic fundamental topological notions are categorified inside topos theory, and in particular, arbitrary unions of open sets, in the topos theoretic setting, they become colimits. And because you consider arbitrary unions in topology, we need to consider arbitrary colimits in topos theory. Okay. Now we introduce another very, very important notion of category theory, the notion of adjunction between functors. Here is a very nice quote by Saunders-MacLean about adjoint functors and their ubiquity in mathematics. Adjoint functors indeed arise everywhere in mathematics, and not only, in many other scientific contexts. Of course, once suitably formalized. But in order to realize about this, you should get familiar with the abstract notion. So I'm going to present it to you. Okay, so let's suppose to have two categories, C and D, and to have two functors connecting them, a functor f going from C to D, and a functor g going in the other direction, from D to C. We say that these two functors are adjoint to each other if one can establish a family of bijections between the morphisms in D from f of A to B and the morphisms in C from A to G of B for any possible choice of objects A in C and B in D. And the requirement is that such bijections should, moreover, be natural in A and B. Natural in the sense that if I change them by means of an arrow, this should give me naturality squares. Okay, so this is the abstract definition. Notice that the two functors don't play a symmetrical role, so we have to distinguish between left adjoint and right adjoint. So this is the the notation. So we write the left adjoint on the left and the right adjoint on the right. Yes, so this is the fundamental condition that one requires. So when I say naturality in A and B, I mean the following. So we should have bijections for any A and B. And naturality means that, for instance, I'm going to discuss naturality in A, and for B it will be similar. So naturality means that if I go from A to A prime by means of some arrow F, then there should be a natural compatibility between the identification on the first row and the identification on the second row. So induced by this arrow. So you see this arrow F induces by composition, here with F itself and here with F of F, vertical arrows like this. So naturality means that this diagram should commute. Of course, in the case of B, you can draw a similar diagram. And yes, so this is a very, very important notion because, in fact, it determines one of the functors in terms of the other. So if a functor has an adjoint either on the left or on the right, then this adjoint is uniquely determined up to natural isomorphism. This is an exercise that you can do. Now, just a few words on an alternative presentation of adjunctions. So, given an adjunction, this induces two natural transformations called the unit and the co-unit of the adjunction, which are defined as follows. So, we have seen that the adjunction, let me rewrite it here, gives for any C and D, C in the category C and D in the category D, a bijection between these Ohm sets. Now, the idea is to define natural transformations by looking at where the identities are mapped to under these bijections. So you see, if here you take D equals F of C, then of course the identity on F of C becomes an element of this set. So it is sent to something here, which will go from C to G of F of C. So by doing this for any C, I get for any C an arrow, which I can call eta of C, going from C to G of F of C. One can show that this eta of C define a natural transformation from the identity functor on C to the composite functor G composite F. This is called the unit of the adjunction. And similarly, one defines the so-called co-unit of the adjunction. So this is a natural transformation going from F composed with G to the identity functor on D. This is obtained by taking here C equals G of D and looking at where the identity on G of D is sent on the other side. So you see, if I take here C equals G of D, the identity on G of D is sent there to an arrow going from F of G of D to D. And this arrow I call epsilon of D. And similarly, to the case of the unit, one can show that these arrows, epsilon of D, for D varying among the objects of D, define the components of a natural transformation from F composed with G to the identity on D. And what is interesting about this construction of these two natural transformations is that, in fact, they allow us to reconstruct the full adjunction by means of the naturality conditions. Because, in fact, essentially, by the naturality conditions, it suffices to look essentially at where the identities are sent. Because where they are sent determines where every other element, every other arrow should be sent. So, you see, it is a higher level approach to adjunctions. It is a much more compact presentation because instead of specifying all these collections of bijections, you just specify a pair of natural transformations. Of course, just giving two natural transformations without any conditions will not be enough to establish an adjunction, because you see, having an adjunction, it's not just being able to define natural functions going in one direction or another. We, moreover, need them to be inverse to each other. So this requirement of them to be inverse need to be formulated also at the level of these transformations. This actually corresponds to the so-called triangular identities. So these are some kind of algebraic identities that you can require for these transformations, and they correspond exactly to the conditions for the two for the maps that you can define in terms of the unit and the co-unit to be inverse to each other, and so to define bijections. Okay, so again, all of this requires, if you want to understand in full details, I suggest to write down on a piece of paper the verification that if we have an adjunction, then the natural transformations defined from it in this way satisfy the triangular identities, and that conversely, if we start from an arbitrary from two arbitrary natural transformations satisfying these triangular identities, we can build from them an adjunction corresponding whose unit and co-unit will be these transformations. Okay, good. Now let's discuss some examples of adjoint functors to justify, at least very, very partially, Maclane's claim as to the ubiquity of adjunctions in mathematics. Okay, I think that all of you are familiar with free forgetful constructions, like at least in the context of universal algebra. For instance, constructions such as the free group on a set. Let's see that this is an instance of an adjunction between a functor which is called forgetful in the sense that it forgets some structure present on objects on a category, and some other functors which will be the left adjoints to such forgetful functors, which correspond to the free constructions on the objects of the less structured category. But a concrete example will clarify everything very quickly. So we can, for instance, discuss the example of the free group on a set. Okay, so we have the category of groups and group homomorphisms, and the category of sets and the functions between them. These categories are related in various ways, but one very natural way of relating them is taking a functor u, which we can qualify as a forgetful functor, going from groups to sets. So this functor actually is not a very interesting one, because it only forgets essentially that G is a group and only retains the information that G is a set. So it considers G as a set. So basically it takes the underlying set of a group. Okay, so this is a very uninteresting functor. But interestingly, this functor has a left adjoint. And this is much more interesting. It is the free group on a set. So f of S, free group on a set, on the set S. So why do we have an adjunction between them? Well, because we have a bijection between the morphisms of groups from f of S to any group G, and the morphisms in sets, namely the functions, from the set S to the underlying group, the underlying set of the group G. So we clearly have this bijection. In fact, when one introduces the notion of free group on a set, you really introduce this in order to have this bijection. Because what you want to do is to be able to structure S, which is just a set, to generate a group out of it in a minimal way. So essentially, you want that specifying a group homomorphism from that group generated from S to an arbitrary group G amounts just to specifying where the generators, namely the elements of S, should be sent. So you see, it is an example of an adjunction. Then, second example of the list. Well, limits and diagonal functors. Yes, actually, so suppose that C is a category where limits of shape I, for instance, exist. Then we have a limit functor going from the functor category, so the category of diagrams, to the target category C. So this takes just the limit of the given diagram. But we also saw that we had the diagonal functor, which took the constant diagrams at given objects of C. And actually, we have an adjunction where the constant functor plays the role of the left adjoint, and the limit functor plays the role of the right adjoint. Because, you see, giving arrows from delta of C to a diagram F means giving a cone over F with a vertex C. And on the other hand, giving an arrow from C to lim of F. So here we write lim of F as just the vertex of the limit cone. So here we forget about the structure arrows. We take just the vertex. But you see, we have, by the universal property of lim of F, we get this bijection. And so you see that lim is here on the right. So it is the right adjoint, and delta is on the left. In a dual way, we get that diagonal functors are right adjoint to colimits. Okay, good. Let's discuss the fourth example, home tensor adjunctions in algebra. This is another very interesting instance of adjunctions. Let's describe how it works. Last time I mentioned that when you build the tensor product of two vector spaces over a field, actually you are not so interested in the actual construction of this object. What you are mostly interested in is the fundamental property that it satisfies, namely that it turns bilinear maps into linear ones. And in fact, this gives rise, as we are going to see, to an adjunction between the tensor product construction and a kind of Ohm functor. Okay, so let's suppose that V and W are vector spaces over a field K. So we know what this object does. So this is another vector space which has this property that the linear maps from this vector space to any K vector space P are the same thing as bilinear maps from V cross W to P. Okay, now this can in turn be written like this. So taking bilinear maps on this product is the same thing as taking linear maps from one of the two vector spaces, for instance V, to the home vector space and this is a way of formulating things that allows you to appreciate how this construction gives an adjunction between a certain functor taking the tensor product and another functor taking the Ohm because this is this functor evaluated in V, and this is this functor, this Ohm functor evaluated in P. And so from this you recognize the formula for adjunctions. So you see that the tensor product functor is left adjoint to this Ohm functor. These are functors defined on our category of K vector spaces to itself. Okay, very good. Another interesting example of an adjunction is the stone-check compactification in topology. So you can show that if you embed compact Hausdorff spaces into topological spaces, actually the Stone-Check compactification gives a left adjoint to this inclusion. Final example, very important for its applications to categorical logic, is the interpretation of the existential and the universal quantifier in terms of adjoint functors. Okay, so
Can we see this integration and marginalization?
the
Marginalization and disintegration as adjoint factor.
probably, but yes, you should check. But if you have a feeling that two functors are in a natural relation with each other and they go in converse directions, it's very likely that they form a pair of adjoint functors. So you should check that. Okay, so last example is this. So suppose you have a function between two sets, x and y. This function, when you take the power sets, gives, by taking inverse image, an order-preserving function between these posets, which we can consider as categories. Because, of course, there is no doubt that this is order-preserving. Now, if we regard this as a functor between these posets categories, we realize that this has a right adjoint called for all f, and you will understand in a moment the reason for this notation, and a left adjoint called there exists f. How are these adjoints defined? Well, let's start from the left adjoint. The left adjoint takes, so of course they go in the other direction, so we can write them here. So this is for all f, and this is there exists f. So the condition is, so the definition is this. So there exists f applied to a subset of x is simply f of s. So the image of the subset S under the function f. Now, why do we use this notation? Because if you write down the set theoretical formula that defines this subset, you will see that it involves an existential quantification. Because this is what you write. So it's the collection of elements of y such that there exists x belonging to S such that y is f of x. So as you can see here, there is the existential quantifier. In a dual way, we get a description of the right adjoint to the inverse image functor. So here it is defined by this formula. It is the collection of all the elements of y such that for every x such that f of x equals y, x belongs to S. So as you can see here, there is the other quantifier, the universal one, appearing. Very nice, isn't it? It was Lovier that pointed this out for the first time, and it was the birth of a new field of mathematics, categorical logic. Because you see, in this way, he was able to capture fundamental logical operations, quantifiers, in categorical terms. Because, you see, once you have this inverse image functor, you have, and whenever this inverse image functor, such an inverse image functor can be defined, whenever it has a right adjoint and a left adjoint, they can give abstract forms of the universal or existential quantifications. So in fact, this fundamental observation was what allowed Lovier to develop logic in the categorical setting, in particular in the setting of toposes. We will see that in toposes, the power sets will be replaced by sub-objects in a topos, and we will have functors of inverse images connecting them, having adjoints on both sides. And we will be able to use these adjoints to interpret logic in a topos.
Is it just, everything is in here is in set, right?
Yes, yes, here I am just giving the version in sets, but later in the course, next time, we will give the definition of these adjoints in a general topos. They exist in a general topos. Yeah. Okay, so useful properties of adjoint functors. Well, we have already mentioned uniqueness of adjoint functors. This is very important, not hard to prove. And another uniqueness, of course, up to natural isomorphism. Another fundamental property of adjoint functors is continuity. Any functor which has a left adjoint preserves limits. Any functor that has a right adjoint preserves colimits. Again, it is a very important result with a lot of applications, but very easy to prove. It's just a few lines of verification. So you can do it as an exercise. This is used really all the time. In particular, we will use it in connection with the treatment of morphisms between toposes. Okay. Now we come to an extremely important result in category theory, not technically difficult at all, but of great conceptual and technical importance, the Unida lemma. The Unida lemma is a result that describes a certain set of natural transformations. This set here of natural transformations from a representable functor to an arbitrary functor in terms of the set of values of the functor at the corresponding object, which represents this functor. Okay, let's discuss how this works. First of all, we observe that for any locally small category C, we can define a functor called the Unida functor. It's actually called the Unida embedding because it is a full and faithful functor, so what's called an embedding in category theory. So this functor assigns to any object of C the corresponding representable functor. So it is a contravariant representable functor because we want to get a pre-sheaf. So we take home towards C. It is a functor because if I go from C to C prime by means of an arrow F, of course, I get a natural transformation, unida of F, between these home functors. So this is simply given by composition with F, externally. Okay. Now, the unida lemma gives us a bijection, which is moreover natural in the two parameters, C and F, between the collection of natural transformations from such a representable to F and the set of elements of F of C. So this is a natural bijection in C and F. How does it work? Well, there is just one key observation that one has to make, is that the naturality conditions are so strong that in fact a natural transformation from such a representable to F is uniquely determined by its behavior at the identity. Let's see why this is the case. So let's call this natural transformation alpha. Now, what does it mean having a natural transformation? It means giving for any object D of C a function which is the component of alpha at D, going from this home set to F of D. This naturally in D. But now the idea is this. So suppose we have an element here of this set. I can regard this element as an arrow from D to C with respect to which I can formulate a naturality condition. So I write it here, so F goes from D to C. So I can write this naturality square, where here it's in connection with the object D, and here it will be in connection with the object C. So here I will have alpha of C, and here F of C. Now, because F goes from D to C, here it goes in this direction. So here I have F of F, and here composite internally with F. But now, the commutativity of this square tells me that if I take here the identity is sent here to F, and then there it's sent to alpha D of F. But the result I get by following this path should be the same that I get by following the other path, by commutativity. So I can also go first here, and so this is alpha C of the identity on C, and then I go up here, and I get F of alpha C of 1C. And this should be equal. Now, if you look at this equality, actually it tells you that the value of alpha D at F must be equal to that. I have no choice on how to define alpha at D once I have fixed the value of alpha C at the identity. This is the key argument for proving the unida lemma. Then, of course, there are a few routine verifications to make, but this is the key idea. So basically, it is based on the double role that elements of home sets play, because you can regard them both as elements and as arrows with respect to which you can formulate a naturality condition. And it is this double role that gives rise to this kind of equalities. Okay, so from the lemma, it is an easy corollary that the Yoneda embedding is full and faithful. Remember the notions of full and faithful functor from last lecture. Another very important corollary of the Yoneda lemma is this characterization of representable functors. I told you last time that representable functors are very important because when you discover that a functor is representable, essentially it means that all the information about that functor is actually condensed in a single object, which is the object representing it. So it's very important in any concrete mathematical situation where you have functors that carry a significant amount of information to wonder whether they are representable, to try to represent them, possibly by extending them to suitable categories, because it might happen that typically, I mean, if you work with restricted categories, you will not have presentability. It's very rare that a functor, like a random functor that you take, is representable. But what you can try to do is to, for instance, extend from your category to a bigger one, extend your functor, and try to represent it in the bigger context. And because if you're able to represent a functor, basically you have a very full understanding of it, as also clarified by this criterion. So this criterion tells you when a functor is actually representable. It is an easy consequence of the Yoneda lemma. So let's read the statement, and then I will draw a picture that will clarify things, hopefully. So a functor is representable if and only if, well, first let's recall, technically we say that a functor is representable if it is isomorphic, if it is naturally isomorphic to a home functor. So a functor is representable if there exists some natural isomorphism with a functor of this kind. A functor associated with a particular object, let's call it C0. Now the criterion says a functor is representable if and only if there exists such an object, C0, and an element of the set of values of the functor at that object, such that essentially all the other values of the functors at any other object C are derived from the value of the functor at that particular element x0. So the situation is this. So you have here your, say, C0 and your element x0, and then you have other objects of your category, and inside them you will have elements. So of course this is f of C, this is f of C prime, etc. And basically what we have is that for any x belonging to f of C, there should exist a unique arrow f from C to C0, such that f of x0 is equal to x. So you see, from this picture, you really see that the object C0 and the element x0 there, which is called the universal element, actually generates the functor, because all the values of the functor elsewhere are just obtained from that particular element under deformations given by arrows connecting the objects where the elements live to the universal object. So you see here we will have things like this, you see. So this is, in a sense, the center of symmetry for the functor. So once you understand that, basically you understand the full behavior of the functor. This is why it's very, very important to try to investigate representability for functors arising in concrete mathematical situations. Okay. Now, I would like to quickly present some other categorical characterizations of familiar set-theoretic constructions. So first of all, the construction of function spaces in sets. So given two sets, we can always form the set of functions from one set to the other. Now, we can formulate a universal property enjoyed by this construction. It is given by this bijection. You see, the functions from a set Z to this set of functions from X to Y are in natural bijection with the functions from Z times X to Y. And of course, this bijection is natural both in Y and Z. So it gives an adjunction. So taking the exponential, taking the set of functions from a given set X to a variable set, this operation defines a right adjoint to the functor that takes the product with the set X. So this invites us to define this categorical notion of exponential of an object in a category. So suppose that in your category you have binary products, then we define an exponential for a given object of this category as a functor from the category to itself, which is right adjoint to the product functor. Of course, by taking the co-unit of this adjunction, we get an evaluation arrow, which corresponds really to the evaluation function that we have in set theory. You see, it takes an element of x, a function from x to y, and it gives the value of that function at that element. So again, it is captured categorically. Definition: a category is said to be Cartesian closed if it has finite products and exponentials for any object. We have already encountered two fundamental examples of Cartesian closed categories. Of course, the category of sets, because of this, and the category of small categories. What is the exponential of two categories? It is the functor category. You can show that it is this. Exponentials can be concretely built in categories of pre-sheaves by using the Yoneda lemma. Suppose that you don't know how to define them. Well, you can use the Yoneda lemma and say the value of this exponential at an object C should certainly be the same as the value of this home functor. So you take the natural transformation from the representable functor associated with C to this functor. But then you use the universal property of the exponential to turn this into that. And it turns out that this definition works. So you can make the verification that indeed, by defining the exponential in this way, suggested by the Yoneda lemma, you see the Yoneda lemma doesn't guarantee you that it will work, but basically it is a uniqueness requirement. So you know that if it exists, it should be like that. Of course, then you have to verify that it really works. It works, so you can then show that you have a natural bijective correspondence between the natural transformations like this and this, so that we have the universal property of the exponential. So we are not really going to use this later in the course, so I'm going to be quick on that.
Just,
Yes.
when you said the value of the exponential, it's the value of the mapping to the set of functions?
No, so here you have an the exponential is an object of the pre-sheaf topos. So it is a pre-sheaf. And here I am evaluating this pre-sheaf at an object. So this is a set. So the unidal lemma gives a bijection between this set and this other set. So it's curious, this kind of this use of the unidal lemma, because you would expect to always use the unidal lemma in the direction from the abstract to the concrete. While here, you start from the concrete and you go to the abstract, and it is what you need in order to get the idea of how to define it. And we will see another application of UNIDA in the same spirit in a moment for defining the subobject classifier in a category of pre-sheaves. But before that, let's pause a moment for introducing another important notion, the notion of Heyting algebra. So if we have a lattice, we can regard it as a preorder category. So a lattice which, when it is regarded as a preorder category, is a Cartesian closed category, is called a Heyting algebra. Of course, Heyting algebra existed well before the introduction of categories, but it is a nice way of presenting this notion in categorical terms. So a Heyting algebra, for those of you who know about logic, is a notion that provides the algebraic semantics for propositional intuitionistic logic in a similar way as Boolean algebras provide such a semantics for classical propositional logic. In a Heyting algebra, because the law of excluded middle no longer holds, you no longer have a complement for elements. So in a Boolean algebra, you have a notion of complement for any element. So this complement is defined by the two conditions that the intersection should be the bottom element and the union, the join and the meet. The meet should be the bottom element and the join should be the top element. Now, in a Heyting algebra, you no longer have that. But you share most of the other features of Boolean algebras. In particular, as in the case of Boolean algebras, you have a notion of implication between elements, satisfying this adjunction. So you, for any pairs of elements x and y, you have an element denoted like that, which satisfies this adjunction. So for any element z, z is less than or equal to this if and only if z meet x less than or equal to y. You can think about this element as the biggest one that when it is intersected with x is less than or equal to y. Fundamental example of Heyting algebra, the collection of open sets of any topological space. It is not a Boolean algebra, because if you have an open set, the complement of this open set is no longer open. So you can take it in the lattice of subsets. This is actually a Boolean algebra, but if you consider just the open subsets, this is only a Heyting algebra. What is this operation in that case? Well, if you have U and V open sets, U implies V is the union of all the open sets W such that W intersected with U is contained in V. More generally, you can show that every frame, meaning a complete lattice in which the infinite distributive law of like infinite joins with respect to finite meets holds, any frame is a Heyting algebra. So the definition of the Heyting operation is the same. Here you replace unions by joins and intersections by meets. Of course, any Boolean algebra is a Heyting algebra because you see in classical logic, this is the same as not x or y. And so you see, if you want to define the heightening operation, you can use the complement operation in the Boolean algebra, and it gives you what you need. So in particular, we had a notion of pseudo-complement of an element in a heightening algebra, but it's not a full complement. So it is just the biggest element which is disjoint from the given element. But there is no guarantee that when you take the join of that element with the pseudo-complement, you get the top element as in the classical case. So this is what, because this would be the law of excluded middle, you see. This is the law of excluded middle. Either x or not x. In fact, you see, you realize already from these examples the inadequacy of classical logic with respect to geometrical situations, because you see, whenever you have a topological space, the logic which is naturally attached to that is not classical logic, because open sets don't behave as elements of a set. They behave as elements of a heightening algebra. So the underlying logic is an intuitionistic constructive one. So this law you should forget when you work with toposes. In fact, it holds in some toposes, but most of the time it will not hold. In fact, the whole point of doing topos theory is taking into account distinction between local and global, and valorizing the existence of relations between objects in a category. And you see, when you reason classically in set theory, you really allow yourself to separate things with each other. So you treat elements of a set as things that don't have any relation to each other. This is why when we regard the sets as categories, we get discrete categories. The only arrows, the only relations are the identities. So basically, objects are in relations with themselves and nothing else. But you see, in fact, if you are in a situation like where you have a big set X and some subset S, the law of excluded middle tells you that X can be cut into two parts, what is inside the subset and what is outside. So this is actually a disjoint union. But you see, you can do this because the elements are all separated with each other, from each other. So it means that you can simply cut without any problems. You can use your scissors here and separate things that are inside from those that are outside. This is because every element is by itself, is not related with other elements. Suppose instead that you have just a single relation from something that is between something which is inside and something which is outside. You would no longer be able to cut. And this is why when you do geometry, the logic that comes with it is no longer classical. You no longer can use scissors, because scissors would destroy relations. And you don't want to allow yourself to do this kind of brutal operations. So this is why the logic of toposes in general is an intuitionistic logic and not a classical one. So of course there are toposes in which classical logic holds. These are the so-called Boolean toposes, but most of the toposes that arise in practice don't satisfy this law.
So is it the case like, so you say that in general topological spaces we don't recover this separation principle?
Yeah.
Is it the case like, as an example, in the category of Hausdorff topological spaces, the separation?
No, you would need almost discrete spaces. So you would need, so actually the law excluded middle holds for for this, if and only if every open set is closed, which is a very, very strong property. The spaces with that property are the so-called almost discrete spaces. So no, if you have compact Hausdorff spaces, I mean the spaces that are useful in analysis, no, they don't satisfy this. It's really, they are spaces of like a very, very strange type. They are combinatorial, like as the name suggests, it's really discrete spaces, almost the discrete spaces. Okay, so now let's talk about another important construction which in fact will allow us to appreciate why the existence of a single relation between two objects will actually destroy classical logic and oblige us to reason in terms of intuitionistic logic. So this has to do with the classification of subsets, or more generally subobjects in a category. Now, if we work in our usual category of sets, we can put in bijective correspondence the subsets of a set X and their characteristic maps. So given a subset, we can associate with it the map which sends an element of the set to 1 when it belongs to the subset and to 0 otherwise. Now, you realize that to define this characteristic map implicitly relies on the law excluded middle, because you have to separate between two possibilities. Either the element is inside S or not. And the two possibilities should cover the whole space X. So here we use actually the fact that in sets we work with classical logic. Okay, so by doing this, we get a bijective correspondence between subsets and maps from X to 0, 1. Indeed, 0, 1 can be thought as the object of truth values in the category of sets, because in sets, essentially you have a very basic notion of, very simplified notion of truth, because given an element of X, you have, and you can just describe its relation to a subset S. You have to, in a very simplified way, either the element lies inside or not. So, because you have no relations, the situation is very simple and you have just two possibilities. We will see that in a situation in which instead we have relations, it suffices to have just a single arrow to change the geometry completely and to oblige you to consider a richer collection of truth values. But let's go step by step. So we can formalize this correspondence between subsets and characteristic maps like this. So you can fit them into a commutative square, which in fact is a pullback. So here you put vertically the inclusion of the subset into the set. Here you put the characteristic map. Here you put an arrow which we call true, which picks the truth value 1 from the unique element of this singleton. And here you take the unique arrow from the unique function from S to this singleton set. So you realize immediately that this is actually a pullback. It is a fibered product of sets. Okay, so it is characterized by a universal property. So it makes sense to introduce this categorical definition of a subobject classifier. So in a category with finite limits, a subobject classifier will be something which replaces the arrow which we saw in the previous slide. So we replace the singleton set by the terminal object of the category, and we replace the object of truth value 0, 1 with an object omega. And we call such an arrow true. And so the condition is that there should be a bijection between subobjects of an object A and arrows from A to omega. And so the arrow corresponding to a given subobject is called the classifying arrow of the subobject. So in fact, subobject classifiers can also be interpreted in terms of representable functors as like the objects that represent the functor of subobjects in the given category. You see, so if you have a category with finite limits, you can pull subobjects back along an arbitrary arrow. So you get these maps, you see, between the subobject lattices. These are like the categorification of the inverse image map between power sets. So if you have an arrow from A to B, and you have a subobject of B, you can pull it back along F to obtain a subobject of A. So what you do is really to consider the categorical pullback. So A, B, this is F, and so if you have your subobject here, M, by considering the pullback, actually here you just have to realize that when you pull back a monomorphism, you still get a monomorphism. It's an easy verification. So it defines, you see, a functor like this. And a subobject classifier is, one can show that is just a representing object for this functor. Of course, there is no guarantee in general that in a category with finite limits such an object could exist. But we will see that Grothendieck toposes are categories in which such subobject classifiers always exist. And to realize about this, we start from the case of sheaves. Again, we use the Yoneda lemma to understand how such a subobject classifier could be defined. So here is where we use the lemma. So omega of C by Yoneda should be identifiable with the set of natural transformations from Yoneda of C to omega. But then, by definition of subobject classifier, here I am taking the arrows to omega, from this object to omega. So they should be in natural bijection with the subobjects of that object. But what are subobjects of such a representable functor? They are the so-called sheaves. So we have seen how limits are computed in functor categories. They are computed pointwise. Monomorphisms can be characterized in terms of finite limits. Therefore, monomorphisms can also be defined pointwise. So a monomorphism, a subobject of a functor of this kind, a representable functor, will be the datum of, for every object D, of a subset of this. But, I mean, it should be a subfunctor, so if I go from D to E by means of an arrow G, I should get a restriction of the action of the home functor to the subfunctor. So that's the condition. So the sub-objects of a representable are the collections of arrows towards that object which are closed under composition on the right. This is the notion of sieve. A sieve on an object C is a collection of arrows going to C, which is closed under composition on the right. This property of closure under composition on the right is the functoriality property. So you see, but the condition of being a monomorphism is something that is checked pointwise. So it means that pointwise I should have a subset. So for any D, S of D should be a subset of home DC. Good. So as earlier, the Unida lemma gave us very good input on how to define omega. So omega of C is given by the collection of all sieves on C. So it's no longer 0, 1. It's something much richer. You see, in general, how many sieves you can have. You see, if you have a category which has a lot of arrows, you will get a lot of sieves. So many more truth values than in the classical setting. But the basic structural property of the existence of classifying arrows goes through. Because we can classify sub-objects. So to any subfunctor Q, we can associate a classifying arrow, which will be a natural transformation, so going from P to omega. And it will be given by this formula. This formula is actually very interesting because it tells you that, in a sense, you see, if you pick an element x of P, what you have to do is to consider its behavior with respect to Q, not just at the level where x lies, because x lies at level C. You have to consider what happens when you move from C to any other object related to it. And so, actually, what you have to do is to consider the collection of all the arrows from a given object to C, such that when I move this element along the arrow, I remain inside the subobject. And what you can show is that it works. So it gives a pullback square in the category of pre-sheaves. So let me write down it explicitly. So you have your Q, here P, I have to wait for this to. Okay. So here. So, given an element x of P of C, what you look at is how it behaves with respect to the subfunctor Q in relation to all the arrows that can be applied to it. You see, the element is no longer fixed. It can go, it can be transported by the pre-sheaf over other objects, you see. So you have to consider what happens when you move to these other objects. So this is what you have. And from this you can already understand that, in fact, it suffices to have in your category, suppose you have this category where you have two objects and just one arrow between them. And then, of course, always the identities. So suppose you have this category, which is denoted like 2, the cardinal 2. So in such a situation, what is an object of this category? Well, it is a pair of sets, x0, x1, and so if we call this like this arrow p, this will be x of, no, in the other direction, x of p. And you see, if you have an element of x1, suppose you have a subobject. So a subobject S1, so a subobject of x. So it has two components, the component at 1 and the component at 0. And because it is a subfunctor, this restricts to a map between the subsets. Now, if you have an element of x1, if you want to classify its behavior with respect to S, what do you have to consider? Well, you have to consider both what happens at level 1 and what happens at level 0. It's no longer sufficient to look at what happens just, you see, at one place independently from the other place, because the two places are related, you see, and you cannot forget that, as you do in sets. You have to take that into account. So if you have your element here, basically, if you think about it, there are three different possibilities that can arise, because the element can belong to S1, and therefore, if it belongs to S1, its image under this arrow will also belong to S0 by factoriality. But if it doesn't belong to S1, it is still possible that when I move from level 1 to level 0, it belongs to S0. It is possible, and it is also possible the contrary. So it is possible that it belongs to S0, but it is also possible that it doesn't belong to S0. So how many possibilities do I have? 3. I no longer have 2 possibilities. I have 3. At the level of S0, I still have just 2 possibilities. So indeed, the subobject classifier in this case is just at level 0 is 0, 1. But at level 1, it is 3 values. Because these are the 3 possibilities that can arise. So you see, I wanted to discuss this example because, of course, this is the very general treatment. But if you understand this example, I think you understand much of the whole spirit of this theory. Because you see that the existence of a single relation already brings you away from classical reasoning. Because you see here, if you consider this situation, you have a situation where you have x, which doesn't belong to S1, and its image, which belongs to S0. So you see, but the two, you see, are related. by the arrow from 0 to 1. So you see, you have a relation between something which is inside and something which is outside. And this is why you no longer have the law of excluded middle. Because if you had that law, it would mean to destroy this relation. And you cannot do it. So I suggest to you to calculate, to enjoy calculating these sub-object classifiers for some more complicated categories here. So here we are still working with pre-sheaves, not in arbitrary toposes, which will introduce a further degree of refinement. But it's already very interesting, because we already go beyond classical logic. Okay, I think it's all for today. I will just conclude with a definition. The notion of elementary topos, so this is a generalization of the notion of Grothendieck topos, and which admits a first-order axiomatization. So an elementary topos is, by definition, a category with finite limits, exponentials, and a sub-object classifier. And I can anticipate that in an elementary topos, one can interpret a full finitary first-order logic by using all the categorical reinterpretations of set-theoretic notions and constructions that we have examined. So these are examples of elementary toposes. In fact, next time we will see that these are actually examples of Grothendieck toposes, which are a particularly important class of elementary toposes, which will be the main focus of the next lectures. Okay, so I think that's all for today, and we resume next time with a treatment of categories of sheaves and morphisms between them.